So what do we need to know? We've talked a little bit about this already, okay? So the endocrine system is basically a system of glands, okay? And these glands are going to secrete hormones, and hormones act as messengers, okay? They act as messengers that go to a specific target. So in the nervous system, we were used to talking about an effector, right? An effector is either skeletal muscle, cardiac muscle, smooth muscle, glands. In the endocrine system, we talk about a target. It's kind of similar to an effector, okay? So hormones have targets. They get secreted in one area of the body and they use your bloodstream to get wherever they need to go in order to produce a desired effect, okay? So once they hit the target and they interact with that target, they then begin some sort of physiological response in that particular location. But the hormone just acts as a messenger to kind of trigger that response to occur, kind of thing, if you will, okay? Okay, so the endocrine system interacts with the nervous system as well, and they both function pretty similarly, right? In that they both activate different parts of the body depending on where you are, okay? So if we're talking parasympathetic nervous system, it's going to be in the craniosacral regions of the body. If we're talking sympathetic, it's going to be in the thoracolumbar area of the body. Hormones, again, are going to travel wherever they need to go, not at that same location, and stimulate some sort of desired effect. Okay, so it's similar to the nervous system in terms of function. But if you had to compare endocrine system versus nervous system, which one do you think would be faster in terms of a response? The nervous system, right? Yeah, because you're using electrical impulses. Endocrine system has to use hormones, which have to be secreted first. They've got to go into the bloodstream, travel where they need to go, provide some sort of trigger to overall result in a desired effect. So the endocrine system is, yes, inherently going to take a little bit longer, okay? Okay, so it's slower. Why do we need an endocrine system? Hormones are going to help us maintain our happy medium, okay? With different responses. You'll see that it controls our growth. So we have growth hormone as an example that can control cellular growth. It helps maintain our metabolism. It can speed it up or slow it down. It helps us respond to stress. Okay, too much stress is not a good thing, but intermittent stress is okay, like taking Bio 220 in the summer. All right. And then blood chemistry, okay, because we know how important it is at any one moment that our blood chemistry be within normal limits. Because anything that goes askew, your body is going to mount some sort of a response, okay, in order to bring you back to homeostasis, which is your happy medium, okay? So we talked about this before, but again, repetition is key. So the difference between an endocrine gland and an exocrine gland, okay? So endocrine glands are going to secrete hormones. Hormones use the bloodstream, and they're going to respond by providing an effect at a distant target. Okay? So exocrine glands then secrete products utilizing a duct, which means it's going to be a product that's secreted locally. Okay? So that gland is in direct contact with its ultimate target. So give me some examples of exocrine glands. Sorry. What's an example of an exocrine gland? Salivary gland. Okay, what else?
Sebaceous.
Oil glands. Yep. Sweat glands. Right. What about your lacrimal gland in your eye? Right, same thing. Okay, so those are all exocrine glands. So they're secreting their products close by. Okay, and those products are not hormones. All right, endocrine glands secrete the hormones. Okay, so this picture basically summarizes, top to bottom, all the organs that we're going to talk about and what they're responsible for, okay, in the endocrine system. Okay, so again, let's repeat a little bit here. So how do hormones work? Okay, so They get secreted by one area of the body, and they go through your bloodstream to their intended target. And once they latch onto that target, they can induce some sort of physiological effect. Okay? So, hormones are specific for their certain targets. So there's only receptors that are sensitive to certain hormones. Okay? So hormones can have different effects on different targets. So if a hormone, for example, has more than one target, okay, it may induce a different effect at target A versus target B, depending on the situation. Okay? And so this is what I mean by the trigger. So a hormone has to attach and bind to a receptor that's sensitive to it on a target, and then the next step is that cell is going to undergo some sort of event because the hormone triggered it to do so, okay? All right, so there's 3 different ways that hormones are secreted into your bloodstream, okay? Humoral, neural, and hormonal, all right? So let's talk about each one. Okay, so humoral is basically where a gland is going to secrete a hormone in response to some sort of ion change in your bloodstream. So it's either responding to ions or it's responding to nutrient levels, okay? That is called a humoral stimulus, okay? So the example here is the first column, okay? On the back side of the thyroid gland, we have a gland, and we'll talk more about this. This is just a summary. Is a parathyroid gland. And the parathyroid gland is sensitive to calcium levels in your body. So if your calcium levels in the body get too low, that's going to trigger the parathyroid gland to secrete a hormone. Okay? And that hormone is called parathyroid hormone. Okay? But we'll talk about that again. This is just a summary. So what triggered the parathyroid gland to secrete its hormone? Well, you had too low of a blood calcium level. That is a humoral stimulus for secretion. Okay? All right, so the second example is neural. Neural sounds like nerve. Okay? So the best example of a neural stimulus in the endocrine system is the adrenal medulla. Okay, we talked about the adrenal medulla. We said it was an extension of the sympathetic nervous system. So, what triggers in this second column here the adrenal medulla to secrete its hormones? Well, a nervous impulse, right? An action potential coming down that preganglionic fiber. It's going to synapse on those cells that we talked about and induce hormone release into the bloodstream, specifically epinephrine and norepinephrine, which is your body's adrenaline. Okay? But what triggered the adrenal medulla to secrete those hormones was a nervous or neural stimulus, okay, by the sympathetic nervous system. Okay, so the last example then is hormonal. And a hormonal stimulus is a hormone secreted by one gland triggers another gland to secrete its own hormone. Okay? So the example here is the anterior pituitary gland. So the anterior pituitary gland secretes hormones. And those hormones have targets. And the 3 target examples here that we'll talk about again in future slides is the thyroid gland, the adrenal cortex, and your gonads, which is your testes in males and your ovaries in females. Okay? So each of these glands are endocrine glands. So they secrete their own hormones. Okay? But what triggers them to secrete their own hormones is the anterior pituitary gland secreting a stimulatory hormone. Okay? So that's called a hormonal stimulus. All right. So those are the three ways that hormones are secreted. Now, what triggers hormones to be secreted, okay, like we said, it's either neural, it's going to be hormonal, or it's humoral, okay? Because we're not constantly secreting hormones all the time, there has to be some mechanism that's employed in order for your body to know when to stop secreting hormones. Or conversely, when to start secreting hormones. Because you don't need them all the time rolling around in your bloodstream, okay? So, what hormones use is they use what's called negative feedback, okay? So negative feedback is if the concentration of something, okay, for example, the concentration of a particular hormone in the body is below a desired amount, then that's going to trigger more of that hormone to be secreted, okay? So the overall effect is opposite of what initiated it in the first place. Okay, so if blood concentration of a certain hormone is too low, that's going to trigger more hormone to be secreted in order to increase the concentration of that hormone. So the overall desired effect is opposite of what triggered it in the first place. Okay? So if your hormone levels, for example, in the body exceed a point, so you have too much of a particular hormone rolling around in the body, your body is going to stop it in order to get the volume to go down back to a normal level. Okay, so the overall effect is opposite of what initiated it in the first place. Okay. So great example here, let's talk about blood sugar. Okay, and I'll repeat myself on this picture because we have another slide with this picture. Really like this picture, summarizes a lot of the concepts we're covering here, gives you a great example of negative feedback, okay? So be very familiar with this picture in terms of being able to describe it, not necessarily draw it, but describe the concepts. So let's talk first about high blood sugar, okay? So in the body, maybe you just went to In-N-Out, you had a 4x4 animal style fries and a Neapolitan shake. So you upped your blood sugar levels to higher than normal, okay? That's gonna trigger your pancreas to secrete a hormone, okay? What type of stimulus is telling the pancreas to secrete a hormone? It's a humoral stimulus because you're having too much sugar in your blood. That's a humoral stimulus, okay? So the pancreas then is going to say, oh, okay, too high a blood sugar. I'm going to secrete a hormone. That hormone is called insulin, okay? Insulin has two targets. The first target is your blood cells, okay? All the cells of your body. And insulin is going to tell your body cells, hey, there's way too much sugar rolling around the bloodstream. Take some in for me, please. Absorb some sugar. So your tissues are going to absorb some sugar because insulin is triggering that response, okay? Insulin is also going to target your liver because your liver is a huge sugar bank, okay? It filters your blood, it's a huge filter, but it's also a big sugar bank. So insulin is going to target the liver and it's going to tell the liver, hey, there's way too much sugar in the bloodstream. Can you convert it into the stored form of glycogen? And the liver can say, yeah, sure, no problem. So the liver is going to take sugar out of your bloodstream and convert it into a storable form called glycogen. Okay? So the overall effect for both of these targets is to lower blood sugar. Okay, back down to your within normal limit values. And once your blood sugar hits those normal values, the pancreas is going to stop secreting insulin. Okay. Okay. And this is a great example of a negative feedback loop, okay, which is what hormones employ. Again, on this picture, notice that the color of the arrows are different. So the insulin pathway with pancreas is more of like a bluish arrow. The second example is low blood sugar, which is more of like a gray arrow. So say, you woke up in the morning and you're stressed out about the practicum and you decided not to eat breakfast. Okay, so you're giving your body not enough sugar, not enough fuel, okay? So that's gonna trigger the pancreas. And the pancreas is gonna secrete a different hormone. That hormone is called glucagon. Sounds like glycogen, a different structure, glucagon, okay? Glucagon has one target, the liver. And it's gonna tell the liver, hey, we don't have enough sugar in the bloodstream. Can you break down some of that glycogen into glucose and throw it in the bloodstream? Liver says, sure, no problem. And it does that in order to raise your blood sugar. And once your blood sugar gets back into a within normal value, the pancreas will stop secreting glucagon. Okay. So most of the processes in the body rely on negative feedback. Okay. Okay, so there's also positive feedback. Okay, there's a couple examples in the body where we need to use positive feedback. Okay, one hormone we'll talk about again in another slide here, but I'll just write it just so you guys have it. Is the hormone oxytocin. And oxytocin is a hormone that's secreted in females during childbirth. Okay, so oxytocin is secreted in the brain and it targets the uterus and it tells the uterus to contract. Okay, and it continues to be secreted while a mom is in labor in order to promote uterine contractions, with the overall result being childbirth, right? So once a child is born, oxytocin stops being secreted by that female's brain, and uterine contractions cease. Okay? So that's one example in the body of positive feedback. Another example is clotting factors in your blood. So blood clotting. Okay, so you cut yourself, right? And then what are the cells that are involved in blood clotting? Platelets. Platelets are gonna get signaled, come to the area, they're gonna tell their friends, hey, we got a problem, and you're gonna get more and more and more platelets coming in order to stop the bleeding. Okay, that's another example of positive feedback. And then once the bleeding stops, those platelets move on their merry way. Okay. Okay. Questions about feedback loops? Okay. All right. I'll repeat a little bit of this in a minute. Okay. Another good example of, say, negative feedback in the body is body temperature, right? So when you go to the gym and you start exercising, what does your body instinctively do?
Raise.
So your body temperature goes up, but then what reflexively happens? You start to sweat, right? And you start to sweat because it's your body's attempt to do what? To cool yourself off, right? And so you're going to continue to sweat until you can cool off back to that 98.6 or, happy medium body temperature, and then you stop sweating. The reverse, you come into lab and the air conditioning and the vents are on and it's freezing in there and you forgot your sweatshirt. So you're sitting there taking the practicum freezing, and so what does your body start to do? You start to shiver, right? Because muscle contraction generates heat. And then once you've shivered enough and hopefully you've warmed yourself up enough, you'll stop shivering. Okay? So that's a good example also of negative feedback in the body. Okay. All right, so all I really want you to know from here is we have two different categories of hormones, okay? One of them are made from the building blocks of proteins, which are amino acids, and the other ones are synthesized from cholesterol, which is made by the liver, okay? So the protein hormones or the amino acid hormones are hydrophilic, okay? They're water-loving, which means they're gonna have a really hard time crossing a plasma membrane, right? Because the plasma membrane has hydrophobic tails in the middle of it. So amino acid hormones cannot penetrate a target cell. It can land on the membrane and then trigger events within that cell, okay? Now, steroid hormones are lipid-based, so they're hydrophobic, okay? They can go across the plasma membrane because they're hydrophobic. So they can go into a target cell and induce some sort of an effect. And sometimes they may even go to the cell's nucleus and cause translation of certain proteins, So it's just two different classes with two different effects. And it's just based on whether they're hydrophilic or hydrophobic. Can they cross the plasma membrane or can they not? Okay, so now begins our list of organs, the kind of hormones that they secrete, okay, where those hormones go and what happens when they get there. Okay, which is pretty much summarized on the handout. Okay, so the pituitary gland we've looked at in lab, okay, we know that we have, well, it's called the hypophysis. We know we have two different regions. We have an anterior pituitary and we have a posterior pituitary. The adenohypophysis and the neurohypophysis, okay? Two different tissue types. The anterior pituitary gland, okay, usually has a different color than the posterior. And that's because the anterior pituitary gland is glandular tissue, which means it's going to secrete something. So it's the endocrine portion that is going to secrete hormones. The neurohypophysis usually is colored the same exact color as nervous tissue because it's an extension of the nervous system. Okay. And it's going to store hormones and secrete them, but not make them. And I'll repeat myself again on that. So the neurohypophysis is like a storage vesicle for hormones that are made elsewhere. Okay, but the neurohypophysis does not make hormones itself. The anterior pituitary gland does. Okay. Okay. And we know the infundibulum is a little stalk that it sits on, and the hypophyseal fossa, all from way in the beginning, is that indentation on what bone? Hypophyseal fossa, where do you find that? Sphenoid bone? Mm-hmm. Yep. Okay. So, let's look at all the hormones. That the anterior pituitary gland secretes, okay? So there's 7 here that the anterior pituitary gland secretes, okay? So, the first hormone, it's kind of nice because the hormone is named for really what it does, okay? So the first hormone that the anterior pituitary gland secretes is called thyroid stimulating hormone, TSH, okay? So I want you to know the abbreviations, but also the formal name, Okay, so I could use TSH on a test, or I could use thyroid stimulating hormone on a test. Okay? So thyroid stimulating hormone, where do you think the target is? The thyroid gland, right. And what it's gonna do is it's gonna tell the thyroid to secrete its own hormone, thyroid hormone. Okay? Adrenocorticotropic hormone, oh my gosh, ACTH, okay? Adrenocorticotropic hormone, where do you think the target is? The adrenal cortex, okay? And it's gonna tell the adrenal cortex to secrete stress hormones. We'll talk about those hormones in a bit. Okay? Follicle stimulating hormone and luteinizing hormone can be kind of grouped together because they target the same organs. They target your gonads. So in males, testes; in females, your ovaries. Okay? They just have different effects. So follicle stimulating hormone is going to target your gonads, testes and ovaries, and it's going to tell your gonads to make gametes. So make sperm or make eggs. That's what follicle stimulating hormone does. Okay. Luteinizing hormone is also going to target your testes and your ovaries, but it's going to tell your testes and your ovaries to secrete sex hormones. Okay, and those hormones are going to maintain secondary sex characteristics. Okay. Okay. The fifth hormone is growth hormone. Growth hormone, we don't have to know it as somatotropic hormone, we'll just know it as growth hormone. Growth hormone is going to target all body cells. And it's going to tell your body cells to do what?
Grow.
To grow, right. Okay. Then we have prolactin, PRL. Prolactin. Okay, so it's secreted from the anterior pituitary gland, and it's going to target your mammary glands, okay, with the overall effect of producing milk production. Okay, and then the last one is melanocyte stimulating hormone. Okay, where do melanocytes live? In your skin, right? And what are they designed to do? What do they make? Melanin, right? Which is a protein that gives your skin color. So melanocyte stimulating hormone targets the skin, tells the melanocytes to start making melanin. So this hormone actually is really highly active when you're a fetus, and when you're developing. So this is an early stage hormone, okay? But man, that anterior to pituitary gland for such a small region, it has a lot. That's a lot of hormones that it's responsible for, okay? So 4 of them, the first 4 are highlighted in red. And they're highlighted in red because we call them tropic hormones. So tropic hormones, okay, are going to target endocrine glands and tell those glands to secrete their own hormones, okay? So, for example, thyroid stimulating hormone. It targets the thyroid gland and it tells the thyroid gland to secrete its own hormone. Okay. What type of stimulus is this? Is it humoral? Is it hormonal? Or is it neural? Hormonal. Right. Perfect example of a hormonal stimulus. Okay. So, okay, so the first 4 are considered tropic hormones because the thyroid gland, the adrenal cortex, and your gonads are all endocrine glands, and they're going to secrete their own hormones in response. Okay, growth hormone targets your body cells. Your body cells are not endocrine glands. Okay, prolactin targets your mammary glands. Melanocyte stimulating hormone targets your melanocytes. Those are not endocrine organs. So those are not trophic hormones. Okay. Okay, so before we start talking about this, let's just look at the picture here. So anterior pituitary gland, we just went over, has 4 trophic hormones, okay? And it's going to stimulate endocrine glands to secrete their own hormones, right? So the thyroid gland, what hormone does the anterior pituitary gland secrete that targets your thyroid gland? Thyroid stimulating hormone. So all of these little dots, that's all thyroid stimulating hormone. Okay. What about the adrenal cortex? ACTH, right? So all those little dots, that's all ACTH. That's going to target the adrenal cortex. And then the gonads?
Luteinizing and follicle stimulating.
Yep, so it's either FSH or LH that's going to target the testes in this example, or the ovaries. And in response, all of these guys secrete their own hormones. Okay? But who tells the anterior pituitary gland what to do? Okay, how does the anterior pituitary gland know what to do? Well, the overall override, the overall commander, okay, is the hypothalamus. So it's the hypothalamus that's going to decide and tell the anterior pituitary gland what to do. And it secretes all kinds of hormones with different names. We're just not learning those names. We are summarizing, okay? So the hypothalamus is going to either secrete releasing hormones or inhibiting hormones to tell the anterior pituitary gland what to do, okay? So if it secretes a releasing hormone, it will probably tell the adenohypophysis to secrete hormones. If it secretes an inhibiting hormone, it's going to tell the adenohypophysis to stop. Okay. This axis, it does the only thing that's what these just mean: hypothalamus, pituitary, thyroid. Hypothalamus, pituitary, adrenal cortex. You don't have to memorize that. That's just not. Doesn't really apply to anything. Okay. Okay, so how does the hypothalamus get its hormones to the anterior pituitary gland? Because hormones travel through what? In order to get where they need to go? They have to travel through your bloodstream, okay? So we have to introduce a term here called a portal system. We're talking about the hypophyseal portal system because we're talking about the pituitary gland. We have a portal system in the digestive system too that we'll talk about, okay? But the definition of a portal system is a set of veins or a system of veins that's separated on either side by capillary beds, okay? So it's a double capillary bed system, okay? So these hypothalamic neurons, okay, the neurons in the hypothalamus are going to make the hormones. They're going to make either releasing hormones or inhibiting hormones, okay? Those hormones are going to be released from those axon terminals into the first capillary bed, okay? And then those hormones are going to exit out the capillary bed into a system of what are called portal veins. Okay, we've already learned the hepatic portal vein in lab. Okay. So from there then, those hormones are going to enter a second capillary bed, and that second capillary bed is in the anterior pituitary gland. So those hormones enter that second capillary bed, and then they can leave. They can enter the anterior pituitary gland tissue and tell it what to do. Either secrete or don't. Okay. Okay, so that's the portal system of how those releasing or inhibiting hormones get to the anterior pituitary gland in order to tell it what to do. Okay, because hormones use the bloodstream to travel where they need to go. So those releasing and inhibiting hormones from the hypothalamus are going to target the anterior pituitary gland. And they get there through a portal system, a hypophyseal portal system. Okay. Okay. Now, the posterior pituitary gland, like I said before, is an extension of neural tissue. That's why it's colored the same as neural tissue. Okay. Okay. Now, in the posterior pituitary gland, we have a special tract. Okay, it's called the hypothalamic hypophyseal tract. Now, how did we define a tract? It's a collection of axons in the CNS. Okay, we're in the brain. It's a collection of axons. It's a tract. It's the hypothalamic hypophyseal tract. Okay. Okay. So the hypothesis, the hypothalamus is going to make two hormones. Okay. It makes releasing hormones and it makes inhibiting hormones, but that's to control the anterior pituitary gland. Now we're talking about the posterior pituitary gland. Okay. So the hypothalamus is going to make two hormones. Okay. The names are here. I'll go over them in a minute. So it makes the two. Okay. Those hormones get stored in the axon terminals of those neurons, which terminate in the neural hypophysis. Okay. So the neural hypophysis is storing those hormones in those axon terminals. Okay. And when the neural hypophysis gets the signal to secrete them, then those hormones will enter the bloodstream and go where they need to go. Okay. So, the posterior pituitary gland, or the neural hypophysis, does not make the hormones, but it stores them and secretes them. Two of them. Okay. The first one is called antidiuretic hormone. What's a diuretic? What does a diuretic make you do? Makes you pee, right? So like coffee, soda, those are diuretics. So antidiuretic hormone. What do you think the overall effect at that target is going to be? If a diuretic makes you pee, what is this hormone going to try and do? Antidiuretic. So it's going to want you to do what? Is it going to want you to pee? No, it's going to want you to hold on to whatever fluid you have, right? Okay, so ADH, antidiuretic hormone, has two targets, okay? It's going to target your kidneys, and it's going to target your small arteries, your arterioles, okay? So, for the kidneys, what do you think it's going to tell the kidneys to do? Is it going to tell the kidneys to secrete, or is it going to tell the kidneys to hold on? Hold on. Hold on to the fluid. We need it. Okay? And it's going to tell your arterioles to constrict. Okay? In order to increase blood pressure and blood volume. Okay? Okay? Because you can't constantly be secreting fluid, right? If you're continually secreting fluid and there's no control over that, that does what to your overall blood volume? It reduces your blood volume. And what does that do to your blood pressure? It drops your blood pressure. And that's not good, right? Because your heart's a pump and it's based on pressure. If it doesn't have pressure, it's not going to function. So there has to be a way to monitor how much fluid you are secreting. Okay, at any one point in time. So antidiuretic hormone helps to control that by applying those two targets. Okay? Okay, and this is mainly water. Okay, so we're talking about water for antidiuretic hormone, because there's another hormone we're going to talk about that's also water, but it's another ion. So this is water only. Okay? Oxytocin, like I said before, okay, it targets the uterus and it tells the uterus to contract. Okay. It also targets your mammary glands, and it tells your mammary glands to secrete milk. So prolactin develops or produces milk, but you need a separate hormone, oxytocin, to actually secrete it. Okay. So this comes into play when new moms start to breastfeed, because you get a surge of oxytocin. Okay. Questions about that? Okay, so the pineal gland we talked about as well. The pineal gland secretes what hormone? Melatonin. Melatonin basically just targets all your body cells, and it really just allows you to regulate what's daytime and what's nighttime, so it helps your sleep cycles. Okay. Which are already a mess being a student, so. Melatonin tries its best to control your sleep cycles. Okay. All right, moving on to the thyroid gland. Okay. So the thyroid gland lives on top of, just underneath your thyroid cartilage. Okay. It's the largest endocrine gland purely, because that's all it is. It's purely an endocrine gland. It doesn't have exocrine properties, it's just a hormone secretor. And it's really involved in your metabolism. So we'll get back to the lower two bullets here in a minute, but let's talk about the thyroid gland first and what it does. Okay? All right, we've looked at this under the microscope, which is nice. So there's a bit of a review here. So we looked at thyroid follicles, okay? And the substance inside each follicle is called what?
Colloid.
Colloid, okay. So, thyroid gland secretes thyroid hormone, okay? Thyroid hormone is specifically secreted from the follicular cells, okay? Which are a majority of the cells in each thyroid follicle. Okay. And thyroid hormone regulates your metabolism and how well you synthesize proteins. Okay. Thyroid hormone is very dependent on, you don't have to memorize T3, T4, don't worry about any of this. Okay. Thyroid hormone is very sensitive to iodine levels, okay, in your body. So in order for it to function properly, you have to have adequate iodine. Now, thyroid hormone, okay, isn't constantly being secreted by the thyroid gland, okay? When it's created as a precursor called thyroglobulin. And thyroglobulin, I just think of its globules of thyroid hormone just waiting to be activated. Those globules are stored in the colloid. Okay, so the inactive form of thyroid hormone is stored in the colloid of those follicular cells, of the thyroid follicles, and it's called thyroglobulin until it transitions into thyroid hormone when the thyroid gland secretes TH. Okay. All right, so you've got thyroglobulin as your precursor, ready to go whenever TH is needed to be secreted by the thyroid gland. Okay, so parafollicular cells, which are blue in the top picture, not as numerous, okay, but parafollicular cells are going to secrete a different hormone. That hormone is called calcitonin, okay? And calcitonin's overall effect is to depress calcium levels, blood calcium levels, okay? So that's the overall effect. It's going to depress blood calcium levels. So what's going to trigger the parafollicular cells to secrete calcitonin. What's the trigger?
High calcium levels.
High calcium levels, right? You have elevated calcium in the bloodstream, that's going to trigger parafollicular cells to secrete calcitonin. Calcitonin has two targets, your bones and your kidneys. Okay? What is it going to tell your kidneys to do? Hold on to calcium or get rid of it? Get rid of it. Okay? Too much in the bloodstream, we need to get rid of it. Go ahead. Okay, kidneys say, sure, no problem. Osteoclasts, okay? What do osteoclasts do again? They break down bone, okay? So calcitonin is going to tell osteoclasts to slow down, okay? Slow down. You don't need, okay? The trigger is elevated calcium levels. We have too much already. So you guys can go take a nap and take a break, go to happy hour, whatever. Okay? We don't need you right now. So they're going to slow down. Okay? And then once the calcium levels in your blood get back down to homeostasis, then the parafollicular cells will stop secreting calcitonin. Okay? Okay. So let's go back to the previous slide where you've got these conditions here. So there's two conditions or pathologies that can happen with the thyroid gland, very common. Some of you have probably heard of these before. If you may or may not have family members that are experiencing it. There's hypothyroidism and there's hyperthyroidism. So hypothyroidism is person's always cold, not really hungry, okay. Metabolism is just way slowed down. Like it's not very sluggish, okay. Now, people that suffer from hyperthyroidism, depending on what parts of the world they're in, okay, if they're not getting enough iodine, so like I said, iodine is a key ingredient in thyroid hormone. If you're not getting enough iodine, that can be a problem, and that can contribute to hypothyroidism. Some people, if you have an excessive lack of iodine, can form what's called a goiter, and that's on this kid's neck here. So it's like a swelling. It's a swelling of the thyroid gland. It's basically an excessive accumulation of thyroglobulin. You've got a ton of thyroid hormone that's just waiting to be secreted, but the gland is just not secreting it. So you have like an overabundant supply. And that causes a goiter, okay, a swelling of the gland. Okay, but not all people that have hypothyroidism may present with a goiter. That's just a symptom that can occur. Okay, typically in areas of the world where you're lacking iodine in your diet. Okay, so you really don't see that in the Americas. You'll see that in like third world countries. Okay, hyperthyroidism is where your like metabolism is on overdrive. Okay, so you're constantly hot. You can eat whatever you want. You just burn it right off. Okay. Very anxious. Graves' disease, again, is more just it's like an autoimmune response. So what happens in hyperthyroidism, or specifically with Graves' disease, is your T cells will mimic TSH. So your immune cells, your T cells, remember we have T cells and we have B cells. Your T cells will start to mimic thyroid stimulating hormone, which is going to trigger the production of more thyroglobulin. And that in turn can cause goiters. But it can also cause what's called Graves' disease, and one of the hallmark signs of Graves' disease is just bulging eyeballs. Okay, there's actually a commercial on TV I've seen recently with a woman that was talking, she has Graves' disease and she was wearing sunglasses during the entire commercial. But she was advertising for medication. So people that have these conditions will have to take certain hormonal medications in order to control their values. Or if someone has their thyroid gland removed, you have to take external hormones for life in order to maintain what the thyroid gland provides you in terms of metabolism. Okay? So T cells mimic TSH, which is where you get the accumulation and the goiters. All right, so now we need to talk about the backside of the thyroid gland, which is where we find the parathyroid gland. So it's these 4 little spots on the back. We identified those in lab. Okay, and the parathyroid gland is nice because it produces parathyroid hormone. Okay. And parathyroid hormone has 3 targets. Okay. But the trigger for parathyroid hormone to be secreted from the parathyroid gland is depressed blood calcium levels. Okay. So as we age, we have more of a tendency to have too little calcium, not too much, right? So calcitonin usually is a pretty dormant hormone as we get older, okay? But parathyroid hormone, okay, is going to get more and more active depending on what our calcium levels are in our blood at any given time, okay? So 3 targets: bone, kidney, digestive system, GI tract, gastrointestinal tract, the digestive system, okay? So for bone, if the trigger is depressed calcium levels, okay, what's it gonna tell the osteoclast to do?
Break down blood.
Break down bone, right, and throw calcium into the bloodstream. Yes, okay. What's it gonna tell the kidneys to do?
Take in more calcium.
Right, hold on to calcium. Don't secrete it because we need it, so hold on to it, don't get rid of it, okay? And the digestive system? It's gonna increase absorption of calcium through your small intestine, through your digestive organs, okay? And usually that triggers vitamin D activity too, okay? So anyone that has like a calcium supplement, I take calcium supplements, they usually have a vitamin D additive to it because you have to have adequate levels of vitamin D in order to properly absorb calcium from your digestive system. Otherwise, calcium will just fly on by and you won't absorb it. So you've got to have adequate amounts of vitamin D. And this is where, you know, your limited exposure to the sun is a natural way to get vitamin D. So that can also assist in addition to your diet. Okay. So it's going to tell your digestive system to increase absorption of calcium because blood calcium levels are too low. And so once your blood calcium levels go back to normal values, homeostasis, then these 3 turn off and parathyroid hormone stops being secreted from the parathyroid gland. Okay, so a little bit of review here, which is nice. So the adrenal glands, okay. Suprarenal, we know they live on top of the kidneys, okay. We know that the adrenal medulla is an extension of the sympathetic nervous system, okay. But now, in addition to the adrenal medulla, we gotta consider the cortex. Okay, so the cortex has a job, but it's different than the medulla, okay. So the medulla, we know, is where preganglionic sympathetic neurons synapse. And they're going to synapse on special cells that act as the postganglionic neurons, okay? We just called them cells. Now we know their name. They're called chromaffin cells, okay? So those are the modified postganglionic neurons in the adrenal medulla. And those are going to secrete adrenaline, or epinephrine and norepinephrine. Okay? Those chromatin cells. Now, the cortex, we didn't look at the layers in lab, so don't worry about the layers. I'm not gonna get into that. But the cortex itself secretes two different hormones. Okay? And the two different hormones belong into two different classes. Okay? One of them is a glucose base, one of them is a mineral base. So cortisol, okay, is a stress hormone secreted in times of stress. Okay? And this hormone is secreted by the adrenal cortex during long-standing stress situations. Okay, so this is extended periods of time of stress, years and years and years and years. Okay, so what it's going to do is it's going to stimulate using your fats and your proteins in order to generate glucose, instead of just pulling glucose from your bloodstream. So the glucose rolling around your bloodstream is going to be safe for your brain, but it's going to start using your fats and your proteins to generate other sources of glucose. Okay? So this picture here, okay, gives you a difference between long-term stress and short-term stress. Okay? So for long-term stress, right, so proteins and fats are going to be converted into sugars. That's going to increase your blood sugar. Okay, that's not good. That can make you pre-diabetic. Okay. You're going to retain sodium and water in your kidneys because of the stress. And if you're retaining fluid, what does that do to blood pressure? It goes up. Okay, so that's not good. Okay, so you're getting increased blood pressure. And that's from chronic stress. Chronic secretion of cortisol. Okay. Can also lower your immune system too. Okay. So for short-term stress, okay, short-term stress response is adrenaline. Okay. You secrete your body's upper during stress. Okay, but it's a short-term effect. Okay, so heart rate goes up, blood pressure goes up. Okay, the liver is going to provide glucose where it needs. Okay, you're getting dilation of your bronchioles because you want increased respiration because your heart rate's going up, so that's going to increase your respiratory rate. Metabolic rate goes up. Okay, but this is a short-term effect. Okay, it settles down, it quiets once that stressful situation is gone. Okay, versus long-term stress where you're putting your body under stress over an extended period of time. Okay. One pathology that you can get from chronic exposure to stress, to cortisol, is what's called Cushing's disease. And it's the picture on the top of the woman. So you can start generating what's called a dowager's hump, which is the old lady hump on the back. Her face looks really swollen. That's called Cushing's disease, and that's, again, a body's response to chronic levels of stress. So just as much as we tell you guys to study, you also need avenues of relaxation and happiness and exercise and all that good stuff, right? You need wellness. Okay, so the second hormone here is called aldosterone. And aldosterone is similar to antidiuretic hormone, but slightly different. Okay? And it's slightly different because it not only reabsorbs water, like ADH does, but sodium goes along with it. So aldosterone is going to resorb water and sodium ions. Sodium ions go along for the ride. Okay. So aldosterone is going to target your kidneys, and it's gonna basically tell your kidneys to increase the reabsorption of water, and sodium's gonna come along. Okay. And the overall effect is increasing blood volume, which is gonna increase blood pressure. So you don't have to memorize all this with renin and everything. The overall, the driving effect here was reduced blood pressure. Okay. So when you go out, you go clubbing, you go to a party or whatever, and you get your drinks on, okay, alcohol inhibits antidiuretic hormone. Okay. So think about that. If antidiuretic hormone is inhibited, what does that make your body want to do?
Pee more.
Pee more, right? So you break the seal, and then you just keep peeing, right? You keep drinking, you keep drinking, you keep drinking. Of course, you're probably not hydrating at the same time, right? And you continue to pee, and you keep peeing, and you keep peeing, and you keep peeing. What is that going to do to your blood volume?
Decrease.
It's going to go down, and what's going to happen to your blood pressure?
Decrease.
That's going to go down, and you could land in the ER. Okay. So, fun fact, or not so fun fact. Okay. All right. Okay, pancreas. Okay, we've looked at this under the microscope. We've seen this in lab, which is nice. It has exocrine and endocrine function, okay? The exocrine function of it, we'll talk about in digestive system. It secretes digestive enzymes. It helps with digestion, okay? The endocrine function is going to belong to blood sugar levels, right? And in those islets of Langerhans is where we find the cells that secrete the hormones, okay? So, we have alpha cells and we have beta cells. We didn't look at those under the microscope. But we did look at the islets, and the islets is the endocrine function of the organ. So now, alpha cells are going to secrete glucagon, and glucagon is triggered when your blood sugar is too low. So the overall effect is going to be raising blood sugar. Okay, so it's going to target the liver. So the beta cells then are going to be insulin, and insulin is going to target two places that we talked about, body cells and the liver, and it's going to tell your body cells to take up glucose. It's going to tell your liver to convert glucose into glycogen because you have too much blood sugar, and the overall effect is to lower it. Okay, so nothing really new here. I mean, this whole diagram that we looked at before explains that to you, okay? So now you know what cells from the pancreas are triggering the release of what hormone. Is it the alpha cells or is it the beta cells, okay? Okay, so one of the pathologies, which we probably all heard of, when you have an unusual or abnormal response, bodily response to blood sugar, is diabetes, right? And there's two different kinds, okay? Type 1 and type 2. Type 1 usually happens when you're younger, okay? And they usually call it, excuse me, insulin dependent, right? So this is like an autoimmune disease of your T cells. So here goes those T cells again. They either want to mimic TCH or they want to fall off the wagon and do something else. So here, they want to destroy your beta cells. And beta cells make what hormone? Insulin, right? So these people are going to be insulin dependent. They usually have to have an insulin pump, okay, for life. And they have to constantly monitor their blood sugar. So type 2 then is adult onset, And this usually happens because of poor diet and lack of exercise. Okay? And as you get older, okay, your cells might get lazy. Your cells may not be as sensitive to insulin as they used to be. Okay? So these people, if you can change your diet, change your exercise activities, typically you can reverse it, which is a good thing. Okay? So those that have type 1 diabetes, you know, if you're not watching your blood sugar and you're in denial, I mean, you're gonna start getting, you know, circulatory changes in your extremities. And I mean, over the years of me being a PT and working in a nursing home, I mean, I've seen people start losing limbs. Starts with the foot. And then, all right, well, we're gonna have to do an amputation below the knee. And then, well, okay, now it's above the knee amputation. You know, it's like, all right, I guess you're okay losing limbs. Just, you know, there are people that just don't really care. So your body will definitely let you know on that one. Okay, so watch the sugars. Okay. All right, gonads. Almost done here. So, in males, testes, we'll get to females, which is ovaries, okay? Endocrine and exocrine. So the exocrine function for the testes is to produce sperm, make the gametes. Make the gametes. So the endocrine function is to secrete hormones. And the main hormone we know here for males is testosterone. And it's going to target body cells, and it's going to tell body cells to maintain secondary sex characteristics. And it's also, I mean, testosterone also targets the testes and tells the testes, hey, keep making sperm, don't stop. Okay, that's your exocrine function, but I'm here to tell you, keep it going. Okay. So secondary sex characteristics for males is like body hair, you know, increased bone mass, increased muscle density, things like that. Right? Longer vocal cords, which makes for a deeper voice, things like that. Okay. So then for females, okay, ovaries, same thing, exocrine and endocrine. Exocrine function, make eggs. Endocrine functions secrete hormones, 2 of them. Most common one we know is estrogen. Estrogen is going to signal your body cells to maintain female sex characteristics. And it's also going to tell your uterus, so it targets the uterus, and every 30 days, which we'll talk about in reproductive system, a female is going to shed the inner uterine lining, assuming that there wasn't a successful pregnancy that occurred. Okay, so that's what estrogen does, is it's going to tell the uterus to shed that inner lining every month. Now, progesterone is another hormone that goes directly to the uterus and tells the uterus, okay, let's thicken the walls because we could potentially have a pregnancy, a successful pregnancy. So progesterone is just prepping the uterus for a potential implantation. Okay. So the remainder, the other 2 slides here, are just a couple extra structures that I want you to know. We're not going to go over all of this, okay? But for the digestive system, okay? The digestive system has what are called enteroendocrine cells. Okay, well if they're endocrine cells, entero within, they're going to secrete something. And the 2 hormones are gastrin and cholecystokinin, CCK. Okay? Gastrin is going to target the stomach, and it's going to tell the stomach to secrete hydrochloric acid, promoting digestion. cholecystokinin is going to target the gallbladder, which is a storage vesicle for bile. And bile includes digestive enzymes and goodies to help promote digestion. So it's going to tell the gallbladder, okay, secrete some bile into the intestine to promote digestion. Okay, so that's just gastrin and CCK. Okay. Placenta, you guys don't have to memorize, but just FYI, okay, when a female gets pregnant, she starts to secrete a special hormone, human chorionic gonadotropin, HCG. And that's what those pregnancy tests check for. So when you pee on a stick, if it's positive, that means that you're secreting this hormone, and more likely than not, you're pregnant. So that's pretty much that. Skin, don't worry about skin. Kidneys, this is a good one. EPO. Have we heard about EPO in professional sports? Perhaps cycling? Yeah. So the kidneys secrete a hormone. It's called erythropoietin. And it's going to go into your bone marrow. And it's going to tell your bone marrow, start making some more red blood cells for me. Okay. So, what do some of these professional players do is they will extract blood, okay, before a competition. They will literally extract blood into packets that they throw in the fridge, okay? And if you reduce, by doing that, they're reducing their overall volume of red blood cells, right? So what is that triggering the body to do? Make more, right? There's a negative feedback loop right there. You've got low red blood cell volume, the body's gonna be like, dude, make more. So kidneys are gonna, boom, generate EPO and promote more. So, okay, their body starts making more red blood cells, and then what do they do right before the competition? They pull those bags out of the fridge and they reinfuse it, okay? And what are red blood cells designed to do? Carry oxygen, right? But if you're infusing bags of blood into you and your body is already making more red blood cells and already recovering from the blood volume loss that you've given it, what do you think that's gonna do to blood volume?
Increase.
I mean, it's gonna make it, yeah, excessively high, right? Like dangerously high. That's a sacrifice. That can cause, you know, your heart to stop. Okay? So, you know, that's a big risk. And that's why they check for that, because it's super cheating, right? You're using your own physiology to cheat. But hopefully you don't, you know, have a massive heart attack during your race and fall down. You know, that's the sacrifice. Okay.
Was that called blood doping? Is that what they
Yeah.
called it? Yeah. Okay.
Yeah. Yep. And every year they got to get smarter and smarter with how they test for it, and how, because I mean, these, if people want to cheat, they're going to cheat, and they get really good at trying to avoid some of the testing markers that they use for it. So, okay, all right, take a break, go in the sunshine.